Okay, let's get started. Thanks for some of you braving the snow this morning. We will, I promise, finish off our lecture on minimal cognition shortly and move on to the last section in our history on active categorical perception. And then starting next week, we will shift gears and talk about locomotion and how it relates to intelligence in robotics. Okay, any questions about the assignments, differentiable assignments? All going well? Okay. All right, back to minimal cognition. Just as a reminder, we're looking at what you can consider in this lecture a series of physical Turing tests. Let's not argue about what intelligence and understanding is. Let's just try and make machines that exhibit physically more and more of the components of what most of us would consider necessary building blocks of intelligence. We looked at 3 so far, and we're going to tackle the last one today, selective attention. What were the 3 that we looked at last time? You'll have to use one of them to remember what the 3 were. Tuesday wasn't that far back there.
Memory.
Short-term memory, good. And? Self versus non-self discrimination. Kind of important. We all figured this one out a long time ago, but important for robots to take care of. And?
The affordances.
Perceiving affordances, right? What's out there and what can I do with it? Okay, selective intention. This is a tricky one, and this is a little bit further along the ladder towards cognition. Not an easy thing to do. To select moment to moment among the vast wash of raw sensation that's coming into your body all the time, what vanishingly small subset of that raw sensation do you select to attend to? What's important right now? The weight of your clothes on your body, you can feel it, and as I'm talking about it, you've now switched. I forced you to switch attention to feeling the weight of your clothes on your body. Most of the time in the next hour, you're not going to be aware of that sensation because it's not relevant to what's going on right now. But how do we choose what's relevant at any given moment in time? Sometimes it's a relatively trivial matter, and sometimes it's not. Okay. True to form, in these experiments, they're going to look at a minimal, very, very simple version of this problem. We've got our little robot moving back and forth along the bottom of the screen. It's got its 2 rockets that are controlled by 2 motor neurons. It's got its 7 proximity sensors that are supplying 7 numbers into 7 of the neurons that make up the CTRNN inside this robot at every time step of the simulation. And the fitness function, I won't bother going through the math here, is that the agent has to be at the same horizontal position as each object when that object reaches the bottom of the screen. So basically, catch one object and then catch the other object. And I explained what is different, what's difficult about this problem is that at a given point in time, something on the surface seems urgent. It looks like this one is closer to the robot. It should probably attend to this one. But this dashed line, which is representing the falling velocity of this object, is less than the falling velocity of this object. So a smart agent would select to attend to this one, or maybe attend to both for a while to determine which one is going to hit first, and then go chase after this one, catch this one first, and then go catch this one. A student from several years ago actually tackled this in their final project using a different physics engine. How is this robot doing at selective attention? You're watching an evolved CTRNN being played back several times. So this is after evolution. How is it doing? Pretty good, huh? You can sort of see the robot choosing one thing, selecting to attend to one thing, and then, quote unquote, changing its mind and going after another object. When does the robot make these determinations? When does it know which one's going to hit the ground first, or which one is going to pass it first? Lots of trick questions in this class. We can't know. It looks like sometimes it's not sure. Who knows? Who knows? Hopefully this video gives you a bit of a sense for how this is a tricky problem. Yeah? We all have this experience every day, right? You wake up and you're focused on one task and you realize you're not going to finish it, or it's actually less urgent, something else has come up. You got to put that down and move on to something else. And then importantly, when you're finished with that suddenly more urgent task, you have to remember what you were working on before and go back to it. You'll notice in this video that there are considerable periods of time in which the robot cannot see one of the objects, possibly two of the objects in some cases. You can be sure that this robot's CTRNN has recurrent connections, and it's quote-unquote remembering somehow where the object is, or at least on what side of its body the other agent is, and it goes after it. Yeah? Okay. Okay. It turns out that in solving selective attention properly, you're actually solving not just one problem, you're solving multiple problems. In this minimal example, in more complicated versions of selective attention, there's lots of sub-problems you're actually solving that you're not really aware of. The first one in the minimal case, which you hopefully saw visualized in that final project, is the passing objects problem. Something at this moment in time seems urgent, but as you predict into the future, you realize that it's actually something else that's going to become more urgent at a future time. This very simple robot that's got a CTRNN in it, nothing magical, just neurons and neurons and synapses, is already performing prospection. So introspection, you look inward. Prospection, you look outward or forward in time. You're reasoning or thinking about the future. You're planning ahead. Not an easy thing for organisms to do. We can do it, again, imperfectly. This very simple robot, and whatever its CTRNN is evolving to do, is providing prospection. This robot is able to realize, I'm putting everything in scare quotes here because we could argue about what these terms actually mean, but the robot is acting as if it's able to prospect, think into the future, and realize which object is going to hit first and catch it. The other problem it's solving is the object permanence problem. This is why children all over the world, no matter what culture they come from, their favorite first game is peekaboo, right? Holy crap, when something goes in front of my mother's face, when that object moves away, most of the time she's still there. There's this thing called object permanence. Things tend not to just flicker out of existence and come back at some indeterminate point. They tend to stick around, and isn't this fun? Isn't this interesting? You can occlude things for a while, and then they go away, and they're still there. Interesting. Object permanence. This is something that takes a little while to learn, but is obviously very important. When mom's face does go away, this is a big deal. This is a potentially very dangerous situation. I can't see mom. Where is she? Can I remember where she is? What can I do to bring her back? Very, very important for young humans to learn. Same thing for robots. Where is the object? Where is the thing that I was working on before that I now need to go back to and attend to? How do I keep track of all of these things that are happening in the world when the vast majority of the things I care about may not be an immediate view? Kind of important. Okay, so even though we're dealing with minimal cognition and sort of simple building blocks of intelligence, we're starting to sneak up on some that are non-trivial. Okay, we'll come back to these problems in a moment. Okay. All right, as in the previous three cases, we've got our fitness function that's going to select for a robot that catches these two objects when they hit the ground. Evolve, 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 evolve. At the end, they have a population of evolved CTRNNs, some which do a better job of selective attention than others. They're going to pull out of the population that one CTRNN that has the highest value of P. The CTRNN that causes the robot to solve selective attention most of the time. Yeah. And as always, they're going to present us with a visually appealing but hard to digest visualization to understand how the CTRNN enables the robot to solve the task. Okay, here we go. All right. We've got time descending on the vertical axis again. So in each of these 5 panels, we're watching five separate simulations. They're going to replay the CTRNN inside. They're going to replay the evolved CTRNN back inside the robot 5 times, one after the other. And in these 1, 2, 3, 4, 5 trials, they're going to drop the pair of objects in a different way that makes the task increasingly difficult to solve. And they're going to see whether this evolved CTRNN can do it. Yeah? Okay. So in each panel, we've got time descending on the vertical axis. So this is the pair of objects falling. What do you think the 2 straight black line segments represent, given what I've told you about this visualization so far? You'll notice a jagged trajectory. There's also 2 straight trajectories. What are those 2 straight?
They're the position of the 2 objects.
They're the position of the 2 objects. So the slope of the line, where that line is horizontally, is showing where that object is horizontally. And as it's falling, and as time is elapsing in the simulation, that line is descending. So this object here, or this straight line segment, this is the object that was placed above and was a little bit to the left of the other object. That first object fell straight, and the line segment ended at this time. What does that mean? Why doesn't this line segment go all the way to the bottom of the panel? The robot caught the object, and the object hit the ground. So wherever this object was placed, it hit the ground first. What this figure does not show you is how fast this object was falling. It could have been placed very high above the robot and was falling quickly, or it could have been placed a short distance above the robot and fell kind of slowly. So we're not seeing the velocity of the object. We're just seeing the time period in which it was falling, and when the line segment ends, that's when it hit the ground. And either the robot caught it or it didn't. Did the robot catch the object in this case? And how do you know? What's the jagged black line? It's the position of the robot, right? So yet again, we've got a show-off robot. So it's shaking back and forth horizontally underneath this object, which hits the ground first. The robot is acting as if it, quote unquote, knows which one is going to hit the ground first, and it looks like it knows it well in advance. Like in the first few time steps, it's acting as if it's already figured it out. Maybe it has, maybe it hasn't. The fact that it's stitching back and forth directly underneath that object, that's pretty strong circumstantial evidence that yes, it knows which one is going to hit the ground first. And sure enough, the robot is right there when that object hits the ground. What does the robot do immediately after this first object hits the ground?
It goes to wiggle back and forth to the next one.
It goes very quickly to right underneath this the second object, which is only halfway down. It's not even there yet, and it's showing off again, right? It's staying right underneath this object and catches it. This is about as good. It's not optimal, but it's very, very close, right? This is as good as you can probably do. What do the differently shaded parallelograms represent, do you think? This one's a little trickier. Ideas? Yep.
Does it represent like the measured distance from the robot to each object?
It does not represent the distance from the robot to each object. That we can see by comparing the straight and the jagged trajectory.
Is it kind of like which objects it's supposed to be prioritizing?
It could be which object it's supposed to be prioritizing. It's not that.
Is it like the point of view of the robot, like the lines coming out of it?
It's the point of view of the robot. Remember that a robot is not omniscient. It can't see and know everything. It's only getting these 7 floating point numbers at every time step. So as long as the jagged line is inside a parallelogram, that means that the robot can see that object. The light-colored parallelogram represents the object that's going to hit first, and the dark-colored parallelogram represents the object that's going to hit next. So for example, if this jagged line had been out here to the left, it would not be able to see this object. Why are the parallelograms getting narrower as time elapses in the simulation? We know that the parallelogram is telling us something about the perceptual ability of the robot at each moment in time. Why this tapering? Sure, go ahead.
As the objects are getting closer, they're taking up more of the field of view.
As the objects are getting closer, they might be taking up more field of view if they're above the robot. That is true, but that's not what the tapering is representing. The way to read this is when you're looking at the parallelogram, if the jagged line is underneath the parallelogram or within the horizontal bounds of the parallelogram, the robot can see it. But that horizontal bound is getting narrower as time goes on. Why?
I mean, from really far out, there's a wider cone of view versus the minute one.
Absolutely, right? So the authors went to quite a bit of pains to try and represent what are the sensory capabilities and limitations of the robot, and how do those sensory capabilities change as a function of time, as a function of where the object is, as a function of where the robot is moving. Things are complicated when we start to take into account the body in adaptive or intelligent behavior, right? I can see most of the room at the moment. Stuff out here is kind of blurry. Now I can see this chair really well, but I've lost something else. Perception and action is always a trade-off, right? We're always trying to select or decide what to pay attention to, what to do. And from moment to moment, as we're acting and perceiving, we're changing this trade-off based on what we think is important at any given moment in time. Part of the reason why this thing takes up 20% of all your calories is it's constantly recalibrating all the time. What am I supposed to be paying attention to? What am I supposed to be doing? How do I orient my body and my sense organs in space in order to deal with whatever's happening? Yeah, it's exhausting. Okay, so we can see that this jagged line is always within the light parallelogram all the time that object exists. What does that mean? The jagged line is always inside the light parallelogram. What does that tell you about the robot? Relative to this first object.
That it can always see it.
It can always see it. Yep. Can it always see the second object? I see one shake of the head.
Not all the time, but it seems like it has a good idea of where it's going to land regardless.
The jagged line, although of course you can't see the dark parallelogram here because it's occluded by the other one. Actually, this is a good point. The jagged line looks like it's always inside the dark parallelogram, which leads me to think that it always could see the second object. But it's a good point. It may not be able to. It might be that the second object is behind the first object and it's occluded. So, good point. Maybe it can see it, maybe it can't. But certainly, after the object hits the ground, the jagged line is immediately inside the dark parallelogram, and it can immediately see the second object. In this simple case, the investigators placed these two objects and dropped them with particular velocities to make things easy on the robot. The robot could probably see these objects all the time, wasn't too hard. Let's go, sorry, I forgot to talk about the notation down here. So we've got an acronym here for the passing objects problem and the object permanence problem and the not sign inside. So this is a simple problem given the setup here, and the way they've set this up, the robot does not have to solve the passing objects problem. This object here was initially closer to the robot and it hit the ground first. The objects did not pass each other as they were falling. Makes things easier on the robot. And the robot also did not have to solve the object permanence problem. Both objects, I said maybe there was some occlusion here. No occlusion here. But neither object ever passed behind the forward object. Both objects were always in view from the robot's perspective, as long as the robot stayed somewhere where it could actually see both objects. Okay. All right, let's take the same evolve CTRN, put it back inside the robot, put the two objects back at the top of the screen, and drop them again at different positions, at different initial positions at the top of the screen with different velocities. And now they've introduced the passing object problem. So the light parallelogram tells us this first object hits the ground at about this point in time. So this is the object that hit first, but it was the one that was initially further away from the robot. That's not actually visualized in this. We only know that from the notation up here. Yeah? So from the robot's perspective at time step 0 up here, it thought, if it thought anything, it thought that this object was going to hit the ground first, but it didn't. How does the robot do in this case? What is the robot doing in this case? Did it do the right thing? Did it solve the task? I see a lot of nods of heads. The jagged line, the jagged trajectory was right here when the first object hit, and then the jagged line was right here when the second object hit. Good, okay. The robot did what it was supposed to do, just catch the two objects. The fitness function says nothing else, just catch the two objects. Is it doing this kind of in an optimal way? Is the robot showing off? Or is it being lazy? Or is it having a hard time? Put all those things in square quotes. We can't know, but what is it acting like? Ideas?
It's kind of bouncing between them for longer before it might decide on one or the other.
It might decide. It's acting indecisive. If you watch it, it's going back and forth between these two objects. It's acting as if it doesn't know. Again, we have no idea. It might already know exactly which one is going to hit first, where, and when. And just because of some evolved detail of the CTRNN, that's what happens in this particular case. Impossible to tell. But it looks like it's having a harder time until the first object hits the ground, and then it immediately swings over, and now it's showing off again, staying right underneath the second object and catches it. Yeah? Okay, let's make things harder again. So let's reset the C tier and N, reset the pair of objects, and now we are not going to have the passing objects problem. Whichever object is initially closer to the robot above it is the object that's going to hit first. But now we're going to have the object permanence problem. One of the two objects is going to pass out of view of the robot. It can't, no matter where the robot goes, it can't keep both objects in view all the time. What does the robot do in this case?
It immediately goes to the second object, which kind of suggests it already knows where it's going to go.
It immediately, more or less, heads over for this one and is tracking underneath it again. No passing objects problem. So given these three evaluation, it kind of looks increasingly like this C tier and N knows when an object is close, it can very quickly figure out that one's going to hit first, and there it goes. Okay. What happens when it catches the first object? What's the state of play during the time step in which it catches this first object at this moment in time? What does the robot see? Nothing. The first object is just hit, and all 7 proximity sensor values are maximal. I don't see anything. What does the robot do? It immediately starts to head in the correct direction. At some speed, the fact that this is quite a horizontal slope, it's moving pretty quickly and heading towards the object that it can't see, which is falling away from it. It's on its left and it's falling to the left, but it goes fast enough that it gets underneath and it catches it. Okay, whew, close call. All right. Fourth case, now we're going to play the game again. In this case, we're going to have the objects pass one another. The one that's initially closer to the robot is going to hit last. And the object that's initially further away is going to hit first. And by the way, they're going to fall in opposite directions, so the robot can't keep both of them in view. How does the robot do in this case? What does it do in this case? Getting easier to read these at this point? What's happening?
Catches both of them.
Catches both of them, still does the right thing. It's shaking back and forth for a while here. I forgot to mention the dashed line here. So this is related to the passing objects problem. At this point in time, both objects are at equal height above the ground. Yeah? This is the moment at which the objects pass one another. So the robot isn't sure, and then seems sure, and then starts heading in the other direction. And we could argue that this robot is showing off again because the slope seems to be designed, the speed at which it's moving is exactly the right speed so that it gets there just in time to catch the object. The speed at which it's moving is hinting at the fact that it not only knows where the object is going to hit, but when it's going to hit. Even though during all this time, the trajectory is not inside the parallelogram, which means in all this time, the robot can't even see the object. It's running blind. So not only can this robot remember, it seems to have a pretty good memory. It's not just remembering the object is generally over there on the right somewhere. It seems it's acting as if it knows, I can't see it, but I know the object is over there, and it's falling in such a way that it's going to hit there in 3.2 seconds from now, and I know how far away I am from that point. I'll move at the speed that's just fast enough to get me there. Yeah? Okay. Last one. This is, again, they're going to introduce the passing objects and object permanence problem, but they've made things even harder again. How have they made things harder in this fifth and final trial?
The robot only gets to see them both at like the most immediate start point.
There's only this amount of time where the parallelograms are overlapping. It's just during those moments that the robot can see both of them. What does the robot do during this very fleeting moment in time?
It decides really quickly which one's gonna fall.
Absolutely. And it's there. The jagged trajectory starts exactly there. It's there, it's looking at both of them, and then it immediately heads over here. It doesn't necessarily need to. It could have solved, in theory, it could have solved selective attention by looking and then looking at this one and then running blind and looking at this one, running blind again, looking at this one. I don't know about you, but towards the end of the day, I start doing that as well. I'm trying to juggle all the things I need to do by the end of the day. I forget. I go look at my to-do list, go and do something else, forget, come back. We're jumping around. Most humans tend to get increasingly inefficient at selective attention towards the end of the day. Harder and harder to juggle all these things and keep them all in view and in play. Despite the difficulty, the robot immediately heads over there, catches the first object, and again shows off by moving in a way that seems to suggest it knows exactly where and when the second object is going to hit.
Is there a reason why in like when you have the passing objects and the object permanence, in like the harder one, it looked like the robot was like more decisive than in the easier one?
Yeah, interesting. It looks as if it's more decisive. There's much less of this kind of waggling going on. It's a great question, and the answer is who knows, right? It might be at the limit of its ability. It's really stretched in terms of what it can do. So from its perspective, it doesn't have the time or the capacity to mess around. It's got to, whatever that CTRNN is computing, it does it while the robot is moving. It's sort of working at the edge of its competency. That's possible. Or it's just some detail of this evolved CTRNN. That's just how it tends to act in these conditions. In theory, it's possible that another CTRNN evolves that has just as high a fitness value, just a high p-value. And in the simple environments, it's very efficient. It goes underneath and catches, and then immediately goes and catches the other one. But in the harder environments, it does much more of this. It's possible. Hard to say. Could be a great final project to investigate that question. Okay, so that concludes our discussion on minimal cognition. And here, right at the end, we're still dealing with a physiologically simple creature. And yet, already we're using a lot of the terminology that we tend to attribute to much more cognitive things like us. One of the things I find interesting, and many others have found interesting about the minimal cognition experiment, is that you don't need a complex machine and a trillion neural parameters to get arguably cognitive behavior. With the right setup, the right body, the right brain, the right environment, and the right evolutionary selection pressures, you get things that look like the beginnings of cognitive behavior. Whether you agree with me or not, again, that's a subjective matter and is beyond the scope of minimal cognition. Okay. All right, let's move on to lecture 10, active categorical perception. This very term, active categorical perception, is the fifth cognitive building block we're going to look at. We just looked at 4. Let's look at this fifth one. What is active categorical perception? Let me start with a thought experiment. I want you to imagine you're sitting at your desk there. I blindfold you, and I put a series of objects in front of you on the table, and I tell you I'm putting a series of round and edged objects in front of you, and I want you to manipulate these objects to categorize or distinguish between the round and edged objects. Which one are round and which one are edged? Okay, I put this one in front of you, you manipulate it. I put this one in front of you, you manipulate it. I put this one in front of you, you manipulate it. I put this one in front of you, and you manipulate it. What would you say? Or how would you move these objects apart? How would you separate them into round and edged objects?
You look for a corner.
You look for a corner, okay? So which ones? We've got 11 objects here. Which have a corner and which don't? These are pretty simple shapes. Should be an easy answer.
I mean, I guess technically just the first one has no edges, but it might be like hard to tell that the second and third don't, or like have like a tiny edge.
Okay, so the proposal is let's just pick it up and feel it and feel for edges. The minute you say that, for all of us, our motor strips start lighting up and you imagine yourself doing it, and I would come to the same conclusion you would. This one is round and the other 10 are edged. Good? We're done? Seem like a clear-cut case? Not really, right? Somehow it doesn't feel like we've really solved this problem. What are we missing here? It's kind of an unfair test, right? When you look at these, you look at them, you don't manipulate them. It doesn't look like there's a clear distinction between round and edged objects. These objects are designed deliberately to have a smooth gradation between round and edged. So asking you to separate the round from the edged ones seems like an ill-defined problem. It doesn't seem applicable. When you look at them, it doesn't feel applicable. It feels impossible to separate these into round and edged objects by just looking at them. But the moment we bring the body and action into it, the moment you start thinking about picking it up and manipulating it, suddenly it feels like there's a bit more of an answer. Most of us, maybe not all of us, would agree, yeah, if you felt it, this one doesn't feel like it has edges, and then these feel like they have an edge. Some feel like they have more of an edge than others, but these 10 all seem to share one feature in common. They have something that feels like an edge. Think about this transition. We went from passively looking at these things and saying there's no categorization problem to solve here. It's impossible to put some of these things in one bucket and the others in another. But the moment we start thinking about actions, suddenly it feels like there is a potential category. Imagine instead of picking it up and manipulating it, you rolled your palm across the top of these objects while these objects were on the table. Now what happens? Every object I put in front of you, you're blindfold, you put your palm on top of it, and you try and do this. What's the result? You're pushing against the world. The world plus your hand plus this tabletop, this desktop is going to push back. Now what happens? If I start you off with this object and you move your hand back and forth along the top of it, you push down and pull your hand back and forth, what's going to happen? This is not a trick question. Ball's going to roll, right? What about this one? Put this object in front, you put your hand on it, and you push back and forth. Now what's going to happen? It's going to slide. Something is different. What's going to happen to these intermediate 9? Some are going to roll, and suddenly at some point, if I put this one, then this one, then this one, then this one in front of you, at some point when you start doing this, it's no longer going to roll, it's going to start to slide. There's going to be a discontinuous change in the motor sensor loop that you feel. You do something and you feel a sensory repercussion. You're going to have that loop with each of these 11 objects. That loop is going to be more or less the same for a bunch of them, and then all of a sudden that loop is going to change and the object is going to start sliding along the table in front of you. A boundary between two categories, rollable and slidable, suddenly popped into existence that didn't exist when you just look at these things. If you pick up the objects and you rub your thumb along the surface of the object, another category has popped, a category and a category boundary has popped into effect. Active categorical perception is the observation that when we, organisms or machines, interact with the world, categories seem to arise. Categories don't actually really exist out there in the world. This is related to our discussion about affordances. Categories seem to pop up based on our interactions with those objects. Yeah? Fruit and vegetables out there in the world, they're not actually poison or food. They're poison or food to us, depending on what you do with them. Eating a small amount of a given fruit might actually be food. Eating too much of it, it's poison. It depends on you. It depends on what you do with the object. Surviving and thriving in this world in an intelligent manner requires categorization all the time. We need to take everything that we see or interact with in the world and put them in certain buckets. It's important. If we dealt with everyone and everything that we came into contact with as not belonging to a category, it's a brand new thing every time, and we got to figure out what we can and can't do with that thing or person, we're in trouble. Categorization matters. That brings up the next question. Well, how? How do you go about categorizing? How do you learn about things and how to put them into different buckets? You choose how you interact with things in the world. And if you're very clever, if you're very smart, if you're very intelligent, you choose how you interact with things to make categorization easier. Not just do it, but make it easier. You can interact with objects to reduce within category differences. If you choose to solve the problem that I gave you with this action, you're going to reduce within category differences. For the first few of these objects, their particular geometry is going to kind of fade into the background, and mostly what you're going to feel is them rolling underneath your palm. These objects are different, but you're reducing their within category differences. Yeah? Okay. Same thing, if we continue with this action with our palm, we're also magnifying between category differences. Roll, 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 up, slide. There's a discontinuous jump. We can feel that difference. You might alter your strategy if you say, listen, let me interact with the 11 objects again. You might slightly alter your action to better reduce within category differences and better magnify between category differences. You push down on the object. That may or may not reduce category differences. Maybe you feel the edges more, so maybe you press on them more lightly. Roll, slide, you can feel it. Again, a lot of you live in student housing, you share a fridge, your roommate's always stealing your milk, you pull out your milk carton in the morning. There's certain actions you can perform to distinguish what's going on inside the carton, how much milk is in there, and there's certain other actions that won't actually tell you much about what's inside the milk carton. You're choosing all the time actions. Part of the time it feels like those actions are just to forward your goals. Make sure I eat enough, get enough sleep during the day, make sure I stay warm enough, not too cold, and so on. Yes, most of your actions are tailored to that, but you're also performing a lot of actions all the time to subtly do active categorical perception. Yeah? Okay, so how do we teach a robot to do that? We want the robot to be able to distinguish between objects in its environment and push those objects into one category and push all the other objects into another category. We want to make a robot arm that's feeling a whole bunch of objects coming down a conveyor belt and put all the broken things on one side of the conveyor belt and allow all the intact things to continue down the conveyor belt. The robot, assuming it doesn't have a camera, is going to feel a whole bunch of things. How does that robot choose which actions to perform to reduce within category differences between broken things? What are the common things that it should feel that are common across the broken objects? And what else? And how do those actions also reduce differences between intact objects? Okay. How do those actions that the robot chooses magnify the felt differences, the perceived differences between intact and broken objects? Very important for us to solve ACP, important for robots as well. Okay. We're moving beyond the minimal cognition experiments now. This robot is definitely not physiologically minimal. It's got a pretty complicated body. It is a robot arm. And before we go into the details of this arm, how is it going to do active categorical perception? This robot does not have a camera. It's got a whole bunch of sensors in its hand and its arm. We talked about proprioceptive sensors last week. You have proprioceptive sensors throughout your body. They report the orientation of your body in space without you having to look at your body. Okay, so the robot is going to have to choose actions to distinguish between these objects and these objects. We're going to evolve this robot to distinguish between spheres and ellipsoids. We're going to, for every CTRN that we drop into this robot, we're going to evaluate that CTRN 16 times. Okay, here we go. The first of the 16 cases, we move the robot's arm to this initial position, position A, and then we randomly choose one of these 8 objects and put it underneath the robot's palm. And then we're going to have the robot tell us, does it think it's in the presence of a sphere or an ellipsoid? We wait until it tells us, then we reset the arm to position A, choose a second out of these 8 objects, put that underneath the robot's palm, get it to tell us, is that a sphere or an ellipsoid? Do that 6 more times, and we've evaluated this CTRN 8 times. Now we evaluate that CTRN a 9th time. We set the robot's initial arm orientation to position B, randomly pick one of these 8 objects, 9, 10, 11, 12, 13, 14, 15, 16. We're going to evolve CTRNs so that every time we put a sphere under the robot's palm, it tells us sphere, and every time we put an ellipsoid under the robot's palm, it tells us ellipsoid. Yeah? You're probably imagining yourself doing this task right now. Pretty easy for us, right? Feels like an easy task. Maybe it is, maybe it isn't. We could alter this ellipsoid. We could make the major and the minor axis of the ellipsoid more similar, so it's more spheroid. We could make this task more difficult. The more difficult we make this task, the more carefully you have to choose what you do with the object, how you interact with it, to determine, is it a sphere or is it an ellipsoid? What would you do? Here's an action. I take my hand off the object. Probably not a good thing to do. I can't tell. Remember, I can't see. Maybe I do this. Maybe I do this. Maybe I do this. There's an infinite number of actions that you or the robot that could perform that will not reduce within category differences and magnify between category differences. Thinking about thinking is misleading. When I tell you about this task, you're probably rolling your eyes. You're like, this is trivial. Trivial for you. But you've already solved versions of this task many times before. You're able somehow to rule out the vast majority of actions that would not allow you to solve this task. And maybe, if you're awake enough and you've had enough caffeine, you might be thinking of actual things you could do. What would you do? Again, there's an infinite number of strategies that also work.
And you can do the same thing where you kind of like roll it around with the palm and see if it's like moving up and down at all. Because a circle wouldn't, or like a sphere wouldn't.
Exactly. And you were making a circular motion with your hand, right? That's actually a pretty good thing to do. Doing this or doing this might work, but it's somehow not as good. Can you feel that in your motor strip? Right? This is not actually a trivial thing to do. There's a vanishingly small, relatively small set of actions that will work. It's still a large number, but it's smaller than the things that won't work. So in this experiment, this is one of the things the investigators were going after. Can the evolutionary algorithm evolve parameters of a CTRN that result in some of these actions that actually do work? Okay. Let's talk about the body of the robot for a moment. I apologize for those in the back of the room. This might be difficult to see. There is J1, J2, J3, J4, J5, J6, J7 in the arm. What does the J stand for? Joint, right, okay. So there's 7 joints. There's 2 joints in the shoulder. They're simulating our shoulder joint. So our shoulder joint is a ball and socket joint. We talked about this last time. There's 2.5 degrees of freedom in your shoulder. Here's 1 degree of freedom. Here's another degree of freedom. And we've got half of another one. They just put in 2 hinge joints in here. You're working with hinge joints in Pi Bullet. Here's 1, here's 2. So the shoulder can do this. This particular shoulder cannot do this. They've got a 3rd joint sitting halfway along the upper arm. This seems kind of weird. That's representing the fact that you can do this. That's 3. There's joint 4 in the elbow, joint 5 in the forearm, and J6 and J7 in the wrist. 1 and 2. Yeah? So they're actually getting a fair bit of the physiology of our arm correct, which is why this robot is called an anthropomorphic robot. Anthro for human, and in the shape of a human. They're actually building in quite a bit of detail here. You'll notice the hand has a whole lot of blue cylinders. These are a whole bunch of joints in here. And then if you can read this carefully, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 white circles. These represent touch sensors in the palm. Yeah? Most of the touch sensors in your hand are in your palm, not in the back of your hand. Why? You don't have a uniform distribution of tactile information in your hand. Why not? It's obvious, right? Because our hand works like this. You can't curl your most of us can't curl our fingers the other way. Mother Nature was careful. She packed most of the sensation where you need it. Okay. All right. That's the body of the anthropomorphic robot. Let's go through its brain. I like this figure from the paper because it gives a graphical and mathematical description of a CTRNN. Okay, let's count the numbers first. 1 through 7, 8, 22, 31, all the way to 48. There are 48 neurons inside the CTRNN that's controlling this robot. That means there are 48 ordinary differential equations describing how the values of each of these 48 neurons is continuously changing over time as the robot does its thing in the simulation. Yeah? Okay, not so surprisingly, you've seen this before. Some of the neurons are organized into a sensor layer, a hidden layer, and an output layer. You'll notice there are 7 arm proprioceptive sensors. There are 7 joints in the arm. So as these hinge joints are rotating, each one of those 7 joints is reporting out its current angle into this CTRNN. These 7 neurons are receiving a single piece of angle information from its joint. So far, so good? Okay. There are 10 tactile sensors. We went through those already. Those are the 10 tactile sensors in the hand. They're reporting 1 if something is in contact with that part of the hand, and a -1 if nothing is in contact with that part of the hand. And then there are 1, 2, 3, 4, 5 hand proprioceptive sensors. As you're going to see in a moment, all 5 of these fingers are always closed or opened together. They don't actually actuate all of the fingers identically. So they're basically returning, the robot is feeding in 5 numbers, which is the average curvature of each finger. So they're kind of approximating proprioceptive information here. Okay, so we have 22 sensor values, that are arriving into the CTRNN at every time step during the simulation. Those 22 numbers are flowing into the internal or hidden neurons. And what does this particular arrow tell us? What is this arrow? It's a recurrent connection. So this is the investigators telling us we put recurrent connections in here because we think maybe memory is important for solving this task. Maybe yes, maybe no. We'll come back to that. Okay, there are 14 arm actuators. So there are 14 motor neurons distributed along the length of the arm, but there's only 7 joints. That seems kind of weird. Why is that? This is because, again, these investigators wanted to try and make a relatively human approximate physiology here. In your body, all of the muscle groups tend to be arranged in pairs. You have, throughout your body, agonist and antagonist muscle groups. The bicep and the tricep is kind of the most famous example. So when my bicep contracts, my tricep relaxes, and my arm does this. When I want to extend my lower arm, the antagonist contracts and the agonist relaxes. Muscles cannot push, they can only pull on things. So if you want things to extend and retract, you need to have 2 strings or 2 pulleys or 2 bunches of muscles that alternate compression. So what they did is they attached 2 motor neurons to each individual hinge joint, which is kind of overkill. So we've got 2 floating point numbers coming into a hinge joint. They just average those 2 numbers, and whatever the average of those 2 numbers was, that was the desired angle of the joint. Seems like kind of overkill to me, but okay. Okay, 2 actuators in the hand, 2 motor neurons in the hand. These 2 motor neurons are the first of the 2 motor neurons is pulling to close the hand, and the second motor neuron is pulling to open the hand. Agonist and antagonist. In an agonist and antagonistic group, you can have both groups pulling at the same time, which makes the object rigid. You can have neither of them pulling at the same time, and you get ragdoll. If you alternate pulling, you get extension and flexion. Yeah? Okay, so far so good? Okay, nothing too unfamiliar here. The last 2 neurons, neuron 47 and 48, are called the categorization neurons. Why are they called categorization neurons? Remember that in this particular experiment, we want the robot to categorize between spheres and ellipsoids. So this kind of makes sense. I'm going to assume that 47 represents spheres and 48 represents ellipsoids. Maybe if we put an object in the presence of the robot and sensor information starts to flow in, and it arrives at the motor neurons and the robot starts to move, at any point in time, I, as the investigator, can look from outside, and maybe if the value of 48 is bigger than the value, if the value of 47 is bigger than the value of 48, that's the robot telling us it thinks it's in the presence of a sphere. If the value of 48 is larger than the value of 47, that's the robot telling us it thinks it's in the presence of an ellipsoid. This robot doesn't actually talk, but it's got 2 neurons dedicated in its CTRN to tell us, or to tell the fitness function, whether it thinks it's in the presence of the sphere or ellipsoid. Seems like an intuitive thing to do. It is not what the investigators did. We'll see why in a moment. Okay, let's jump from the geometric description of the CTRN to the math. The math corresponds exactly to the geometry and back again. So we've got y sub I, the value of the ith neuron, whichever one of these 48 neurons it is. We've got our familiar time constant here. We've got a single subscript, tau sub I, that reminds us that there are 48 tau values. Every neuron is slower or faster. For the first 22 neurons, they simplified the C-N description. These 22 neurons, they had this term, and then they had a gain next to the inputs. Remember, these are the 22 input neurons. So the rate of change of these neurons is proportional to the particular sensory information they're getting and their laziness. When they don't get sensory information or the sensor value tends to be near zero, these neurons will relax back to zero, but they may relax back more slowly or more quickly. All the other neurons 23 through 48, have the more familiar form. They're lazy, they're faster or slower, their rate of change is dependent on incoming values from the other neurons that range between N and M. N ranges between 1 and 30 for neurons 23 through 30. So these 8 neurons here, they're influenced by the incoming values of the first 30 neurons. These neurons are being influenced by these neurons and these neurons. The incoming values of neurons 31 through 48, these neurons, the rate of change of these neurons is being influenced by neurons 23 through 30. So all of this notation down here, this is just representing the arrows or the connectivity that you see here. Nothing too unfamiliar here. So far, so good? Okay, so hopefully we understand the body of the robot, the brain of the robot. These 2 categorization neurons, still undetermined. Okay, here we go. Here's the math for what these 47 neurons are doing. I'm going to draw a visual representation of what they're doing. Remember that these are C-N neurons, so they're changing their values continuously over time. So we could make things simple by plotting time on the horizontal axis and then plotting the value of neuron 47 as it continuously changes over time. And we could also plot the value of neuron 48 continuously over time as the robot does its thing in the simulation. I'm going to do something a little bit different today. We've got these 2 continuously changing variables. I'm going to put one of them on the horizontal axis. I'm going to put y47 on the horizontal axis. And I'm going to put y48 on the vertical axis. And I'm going to mark 0 and 0. Let's assume at the very first time step of the simulation, the moment we drop a C-N inside this robot and turn on the simulation, let's assume that the initial value of neuron 47 is 0, and the initial value of neuron 48 is 0. So these 2 neurons at time step 0 are 0, 0. Okay. In time step 0, sensory information comes in that propagates through to the hidden layer, depending on whatever the taus are, the gains, the offsets, and the weights. They flow all the way through and arrive at values 47 and 48. Values 47 and 48 are now something different. I don't know what they are. Let's assume this is the new value of 47, and this is the new value of 48 at time step 1. These were their values at time step 0. At the next time step, these 2 neurons' values change again, and again, and again, and again, and again, and again. And if we connect all the dots together, we get a trajectory in phase space. So this is what's known as a phase diagram. It's a way of plotting how several variables change together over time. So as we walk out along this trajectory, we're moving forward in time through the simulation, and the shape of this trajectory tells us something about what these neurons are doing. If, for example, we went back and we started at 0, 0, and we got a diagram that looked like this, hopefully you can realize immediately, you can tell that these two neuron values became positive. They both became positive. They're in the upper right quadrant, and they stayed positive. A trajectory like this tells you, well, the values didn't change too much. A trajectory that just always stays here tells you that these neurons never changed values. They started at 0, 0, and they never changed. So phase diagrams are nice because they give you very quickly an overall view of the behavior of these variables over time. So far, so good? Okay. Let's imagine we put the robot in the presence of a sphere. It doesn't know it's in the presence of a sphere. We've just put its hand on top of the sphere, and it starts moving. And let's assume it produces a trajectory that looks like this. It's arbitrary. Yeah? Okay. Now I'll put an S here for sphere. Now we take the same C turn N, we reset the robot's arm to position A, same C turn N, we pull the sphere out and we put an ellipsoid underneath and we let it do its thing again. We're running a second simulation, so again the neurons start at 0, 0, and it starts to do kind of the same thing. And then these two neurons change like this over the second simulation. So far, so good? I told you that we evaluate each C turn N 16 times. Let's just start with these 2 times. This is the trajectory when the robot was in the presence of the sphere, and this was the trajectory when the robot was in the presence of the ellipsoid D. Question?
Doesn't the fact that you're evaluating it 16 times make it fundamentally not continuous time?
Yeah, correct. Within any one simulation, it's continuous time, but between simulations, you're absolutely right. It's discontinuous.
Okay.
Good point. We do not integrate these 48 ODEs across simulations. It's only within. Yeah, good point. Good point.
Within simulation, there's a time step still. Right?
Okay, I've been hiding this fact. You're right. Computers are not continuous creatures.
That's
Yep.
what I was thinking.
Okay.
There's no way this is continuous time.
Okay, yes. Yeah, exactly. This is not a numerical methods class. So I will just say very briefly, we're going to simulate these ODEs in a computer, but the computer can't simulate them perfectly. It's not really continuous. It's something like this. Yeah? Okay. All right. So yes, I'm cheating a little bit by drawing it as a curve. Okay. All right. So we've got these two trajectories. And what the investigators are going to do, or they wrote a little bit of code, is that they put a bounding box around the last 5% of the time steps of the simulation. So uppercase T represents the total number of time steps. Maybe they ran the simulation for 100 time steps, in which case upper T is 100, or they ran it for 1,000, uppercase T is 1,000. It's not mentioned here. Lowercase t is the current time step. So they're looking at time steps, lowercase t, that range between 0.95 t, so the 95th time step to the 100th time step, or the 950th time step to the 1,000th time step. They're looking at the last 5% of each of these trajectories. Okay, why are they only looking at the last 5%? The intuition here is that they're letting the robot play before it makes its decision. If I put a sphere and ellipsoid underneath your hand, and the minute I started the clock, I wouldn't say, tell me, which one is it? You need time to roll the object and say, oh, it's a sphere. No. Oh, no, it's an ellipsoid. You need time. So they're giving the robot the first 95% of the simulation to quote unquote make up its mind, and then they're going to look at this trajectory and pull out from this trajectory what the robot thinks the object is. So far, so good? Okay. What are they going to do? What does this math here represent? This math represents them putting a bounding box around this last little bit of the trajectory. They look at the minimum value of 48, the maximum value of 48 in this period. They look at the minimum value of 47, they look at the maximum value of 47, and they put a bounding box around it. Then they do the same thing for D. They find the max and the min of 48, the max and min of 48, and the max of 47 and the min of 47, and they put a bounding box around that. Okay, this is getting complicated. Why didn't they just say 47? If the value of 47 is greater than 48, it's an ellipsoid, otherwise it's a sphere. They seem to be going to a lot of effort here to do something. I want you to look at the pair of values of these neurons inside this box and inside this box. Tell me about them. In this example I've shown you here, these bounding boxes don't overlap. What does that mean from the robot's perspective?
The two objects are categorically different.
The objects are categorically different. Close. I wouldn't say categorically different because the robot hasn't made a categorization yet. All the robot has done is, I don't know what it's done, but it's done something and got this result. And then another object was put underneath and it did something else and it felt something different. From the robot's perspective, these things feel different. Not feel in the emotional sense, but the sense of something inside its brain. The value of these two neurons is quite different in this case.
Did they ever do this with hardware?
They did not. I am still trying to convince one of my mechanical engineering colleagues to do this. It would be fun to do this in reality.
What kind of touch sensors do you think they would use?
We're going to talk about soft robotics towards the end of the class, and I have some colleagues who work in this area. They develop robot skins. They develop fabrics in which there are circuits woven into the fabric, and then they literally sew the fabric onto the hand of a robot. So they're trying to approximate what we have.
It's like a capacitive sheet, right?
That's one robot skin is a capacitive sheet. There's lots of different ways to do it. Yeah, good question. Okay, this robot doesn't have that. It's just got these 10 touch sensors inside. And we can now say that in this example, this particular CTRN produced these values for 47 and 48. And for the robot, these two objects felt different. Now, whether they belong to different categories, we haven't got that far yet. This is all that we have so far. Yes?
Is this just like using the fact that like doing the same thing to a sphere and an ellipsoid will like result in like different like
Great point. Same thing, right. Does the same thing, the same action, produce different sensory results? The answer is it depends on the action. This action does not produce, cannot produce non-overlapping boxes.
So how do they know that they wouldn't overlap like to start with?
How do they know that they wouldn't overlap to begin with? Great question. Okay, let's go back to the beginning of evolution. We're going to start evolving. Populations of CTRNNs, and not surprisingly, they're all going to do a crappy job at what we want them to do, which is ACP. Let's assume one of those random CTRNNs at the beginning of evolution causes this action. What does that mean? That means these neuron values here, the robot goes like this, and all of a sudden, all of these 22 go silent, more or less. Not quite because there's proprioceptive, but they go quiet. And so maybe this happens. Then we put an ellipsoid under the robot, and the robot does this again. It took its hand off the object. It can't feel any different. So if we put a bounding box around the S trajectory, and we put a second bounding box around the D trajectory, those two objects feel identical to the robot because it did the wrong thing. Everybody see that? So what do you think the fitness function is that they used in the evolutionary algorithm? What did they want evolution to cause to happen? I think I saw a light go on.
For them to be different.
Them to be different. What's them?
The two boxes.
The two boxes.
Distinct, I guess.
The fitness function is going to evolve C-tier and ends that push these boxes apart. They want to increase or magnify between category differences. We've got 1 minute left, so I want to just put in one last detail. So we've got two trajectories here. Here's the S bounding box. We've got a second trajectory here. Here's the ellipsoid bounding box. But we've got 14 more trials to do. So this is with sphere 1, ellipsoid 1. They take a sphere and put it back under the robot's hand. And now with this second sphere, it does this. And we get bounding box S2. And then we put another ellipsoid. We put another ellipsoid. This is ellipsoid 1. This is ellipsoid 2. We put ellipsoid 2 under the robot's arm. And it does this. And we get D2. I won't do all 16, but there would be 16 bounding boxes, 8 S boxes, and 8 D boxes. We'll just stick with 2 S boxes and 2 D boxes. To finish things off, they're going to put one big bounding box around all the S's. And they're going to put one big bounding box around all the D's. This is the category differences. These two big boxes represent the robot's understanding of the categorical differences between the objects. This is what spheres feel like, and this is what ellipsoids feel like. If these two big bounding boxes are non-overlapping, then spheres feel differently from ellipsoids. Okay. I think this is a good place to pause for today. You have a quiz due tonight. You're working on various assignments. See you on Tuesday. Thank you.